Thank you very much, Supratim, for the introduction, and also thanks for the organizers of the conference for the invitation and the opportunity for me to present my work. Yeah. So this is a topic. The flavor of the topic will be slightly different. It will be mostly to the games part of the workshop. Yeah, not on evolution and so on. So the outline of the talk is as follows. So first I will talk about multi-agent systems and also some review of dynamic game models to actually model strategic interactions in multi-agent systems. Then we talk about an equilibrium concept called as output feedback Nash equilibrium when agents have limited information. Yeah? And we also talk about what are the issues in computing this output feedback Nash equilibrium. And as a remedy, we propose another equilibrium called as a guaranteed cost equilibrium. So then I'll provide conditions for the verification and the synthesis of guaranteed cost equilibrium, followed by some numerical illustrations. So what are multi-agent systems? Basically, if you take applications like smart grid or spectrum auctions or in communications or aerial dogfight in military or rescue operations, or like coordinated hunting and swarming collective behavior in biology, common to all these applications are the presence of, these are large-scale distributed systems which involve basically engineered or biological agents with interrelated objectives. And we also see behaviors such as coordination, self-interest and conflict. And these strategic interactions also evolve with time. Okay? So game theory provides a mathematical framework for analyzing these interactions and towards predicting outcomes. So here I use the cost framework. So duration of agent I is denoted by the variable ui, and all other agents except player I is denoted by minus I. Okay? I think that's a standard notation in game theory. So when agents cooperate or if they have mutual interest, the outcomes are like studied under the framework of cooperative games, or at least the strategic interactions are studied under the framework of cooperative game, where each agent's cost is minimized and over the decision space of all the players. Okay. When agents have mutual interest and there is no cooperation among the agents, then these strategic interactions are studied under non-cooperative games. So in cooperative games, usually the outcomes are Pareto outcomes. In a non-cooperative game, the outcomes are usually equilibrium outcomes. So centralized decision problems are studied under the framework of cooperative games, and decentralized or distributed decision problems are studied under non-cooperative games. And by definition, equilibrium outcome is stable with respect to deviations, unilateral deviations of the players, but that is not the case with cooperative outcomes. Then we also said that most of these multi-agent interactions that I showed in the first slide, they also evolve with time. Yeah? In the sense, decisions taken by agent at one particular time instant will have a consequence in future. Then the question is, how do we model such interactions? So we model those interactions with this dynamic game where at every instant agents are taking actions and influence the evolution of a state, which is usually represented by a differential equation. So here state could be, in case of dogfights, the position and orientation of the agent can be a state. If you are looking at a pollution kind of an example, the total stock of pollution can be seen as a state variable. And agents' actions will influence the evolution of the state. Okay? And at time t, by taking actions, each agent gets incurs a cost that we call as the instantaneous cost. And if you assume that agents are interacting for a period time t, so this is the total cost incurred by the player. And here the duration, in the sense, the play can be for a finite period or an infinite period. This is, in some sense, the description is similar to an extensive form game, but it's a lot more structured. Okay? And these are, so and players, when taking an actions at any point of time, can take actions based on the information that is available to them. Okay? So if players at any time t take decisions based only on the initial state, that particular information structure is called as an open loop information structure. If at any point of time agents have complete observation of the state, yeah, then we call that particular strategy as a state feedback strategy. But if agents have information only about partial information of the state, that is only measurements or partial observations of the state, we call that information structure as an output feedback information structure. So in a dynamic game, the outcome of the game is information contingent. This is not seen in a static game. Okay, this is where dynamic games are different. Yeah, so once I fix the main ideas, so here are some of the standard references in dynamic games. So this is basically to study strategic interactions in military and so on. So this is mainly focused on economics and management science. And this is a standard textbook on differential games for basically theory and algorithm science. So now coming to the focus of today's talk, this is a joint work with my recently graduated PhD student. So this is on guaranteed cost equilibrium in differential games. So here our work is motivated by real world applications where agents may not have complete observations of the state, because usually it's a very rich description, and agents get information through sensors. So they may not have complete observations of the state, but only partial observations. And if the agents are connected in a network, agents may have only local state information, but not the global state information. So if xi is the state of agent I, if I consider the global state to be, I concatenate all the states, I will not have information about the entire global state, but only about k. The question is, how do we model these interactions where agents have limited state information? So we choose a linear quadratic framework. So I assume that dynamics is described is a linear dynamics, and agents have partial observations of the state that's captured by the matrix Ci, where Ci is not is a rectangular matrix with number of rows not greater than the columns. I assume the rank of Ci to be full rank, yeah, and the costs of the costs are quadratic in nature. So I assume Qi to be positive semi-definite and Ri to be positive definite. Okay. This is to impose certain convexity on the cost. And here each agent is trying to minimize his own cost, and there is no cooperation between the agents. So then the natural outcome is a Nash equilibrium outcome, but here with the idea that agents have only partial information of the state. They don't have complete information of the state. Okay. How does that set up eat up information? Here Ci is a matrix which have more columns than the state, than the rows. If X is of dimension n, I'm able to only observe a low dimensional version of the state. That is how I capture the dynamic games with limited information. That is how it is encoded. Is it clear? And the reason why we are focusing on linear quadratic games is because of we want to characterize the existence conditions with respect to the problem data, that is A, B, and so on. And we also want to compute this equilibria. Yeah? Okay. Okay, so now we also restrict the strategies space of agents to be linear in output. Yeah? Then we can rewrite basically the cost in terms of these matrices, which I have to determine now. Okay, then the output feedback Nash equilibrium is defined with the standard Nash equilibrium definition. And the literature, the existing results say that I can compute this Nash equilibrium, output feedback Nash equilibrium, under 3 steps. The first is I have to compute, I have to solve a certain matrix equation called as coupled algebraic Riccati equation. That is, here I have one equation, but one for each player. Okay, where this Pi is a symmetric matrix. So I require that the solution of this coupled algebraic Riccati equation is stabilizing. Okay. Why we need this stability? Because notice that these costs are defined over infinite horizon. I want to keep this cost finite. Yeah. So the stability condition is essential to keep that cost finite. So once I am able to find a symmetric stabilizing solution for this coupled algebraic Riccati equation, I can synthesize player I's Nash equilibrium cost by solving this, player's Nash equilibrium strategy by solving this matrix equation. This is the approach. But what are the difficulties with this approach? The coupled algebraic Riccati equation, even for the full state feedback case, if you observe closely, it has Pi is a variable which is a symmetric matrix, so it will have n into n plus 1 by 2 variables. So this equation is just for one player but have n players. So I have n into n plus 1 by 2 multivariate polynomials of degree 2 with that many number of variables. Yeah. So that means I have to solve these degree 2 polynomials. And as you can see, the complexity shoots up as the state space dimension increases and also the number of players also increase. So there exist iterative methods for solving these polynomial equations, but convergence to a stabilizing solution is not guaranteed. That means that is precisely because the stability requirement is not embedded into the iterative scheme. Yeah. And even if I obtain a stabilizing solution, the Nash equilibrium, we said that can be synthesized by solving this matrix equation, and we see that for exact solvability of the feedback strategy of player I, we require that the solution of the coupled algebraic Riccati equation must satisfy this structural condition that rows of B transpose Pi must belong to the row space of C. And we see that even for games of very small dimension, these conditions are very hard to meet. Yeah, that is, sufficient conditions available in the literature are too restrictive here to compute a Nash equilibrium. So our research question is there a broader class of output feedback strategies that satisfy an equilibrium property? Here the broader refers to the idea that if an Nash equilibrium exists, it must be an element of the new class of strategy I am talking about. Okay, so our motivation here is suboptimality approach. In case of a Nash equilibrium, each player is giving a best response to, everyone gives a best response to each other. That is, player I gives a best response if opponent's strategy is f minus I, player I solves this minimization problem in a Nash equilibrium, and every player does that. But here we look at a suboptimal problem, that is, given opponent strategy, player I has an expectation of what is cost, saying that I know the opponent strategy, I also know what cost I want to achieve. Okay, this delta I is a bound on player I's cost. So here player I is trying to see or find strategies which will ensure that his cost is below this bound delta I. Okay, is it clear? The notion of suboptimality here is player I in this suboptimal notion is not trying to minimize his cost, but rather trying to find all feedback strategies that ensure that his cost is below this threshold delta I. Okay, so that is the notion we are talking about. It's a slightly different behavioral notion compared to the best response. So player I has an expectation that his cost, there is a bound, and player I is looking for strategies that ensure that his cost is below that bound delta. So from a solution standpoint, we see that these two behaviors have different solution sets. Yeah? In the first best response, we already discussed about it. It leads to solving polynomial, it's solving polynomials and also with structural constraints. But the suboptimal problem actually leads to a set of matrix inequalities, and we are looking for a non-emptiness of certain set which is characterized by inequalities. Okay? That is with respect to difference in the solution sets. But with respect to behavioral difference, so we call this response, the suboptimal response, we talked about as a guaranteed cost response. That is, given player I's cost threshold and opponent strategy, player I is trying to find all feedback strategies that ensure that his cost is below this threshold delta I. Okay, so that is given delta I, and opponent's strategy, player I is trying to find this set. So from a behavioral standpoint, a player I's reaction in this guaranteed cost response is little weaker compared to a best response. Why? Because here player I, suppose if opponent deviates from f minus I to f tilde minus I, a best response would move. But in a guaranteed cost response, even if the opponent is changing the strategy, but as long as player I's cost is below this threshold, there is no incentive for player I to move his strategy. Okay? In the sense, with the guaranteed cost response, the reaction of player I to opponent's deviation is little weaker. Okay? So now once we define this guaranteed cost response, we can also now talk about an equilibrium notion with this guaranteed cost response. So we given a cost profile and a strategy profile, a guaranteed cost equilibrium of player I is basically equilibrium strategy of player I should be in the guaranteed cost response of player I, given that the opponents use their guaranteed cost equilibrium strategies. And here the stability is basically no player has an interest in deviating from the current strategy, as each player has achieved a desired upper bound on the cost. So this equilibrium notion is not something new. It was already there in the static game literature with the idea of the name satisfaction equilibrium. Here what our contribution is extending this notion to differential games and also deriving properties and find a method of computing this equilibrium in differential games. Okay, so we have this guaranteed cost equilibrium, but what is its interpretation? How do we interpret this equilibrium? So this equilibrium can be interpreted as follows. We have n players, they have their private, in the sense they have their cost, their cost bounds, delta i's. They can reveal their cost bounds to the social planner, and the social planner will compute this equilibrium and privately proposes to each player what strategies they should be playing. If all other players follow the proposal of the social planner, then player I's cost will be lower than, or at least player I's cost will meet the upper bound by following the proposal of the principal. Yeah? So that is, if everyone is following the proposal of the principal, player I will achieve the cost bound by following the proposal of the principal. Again, here notice there is no communication between the players, but there is some amount of correlation that they are talking to a principal. So in some sense, this concept is similar to the correlated equilibrium in static games. Okay, so now what are the properties? So the properties here, in the sense, if players have very high expectations about their costs, that is, here I mean high expectations means they have a very low tolerance, they keep reducing these bounds, we see that the guaranteed cost equilibrium with very high expectations will shrink. Yeah? So here I mean high expectations means the low values of thresholds. Okay? We can also show that if a Nash equilibrium exists, it is also an element of it is also a guaranteed cost equilibrium for this choice of the cost profile. Okay. Now we can also provide the efficiency result, in the sense efficiency properties of a guaranteed cost equilibrium. So here we use in the literature we have this price of anarchy and price of stability measures to talk about efficiency of an equilibrium. So here I use the price of stability measure, so that is defined as the total cost in equilibrium divided by the total cost in cooperation. So the lower bound is straightforward. We get this lower and upper bounds for the POS for a guaranteed cost equilibrium, and the lower bound directly follows from the idea that in costs in cooperation are the lowest that you can get. Yeah? But the upper bound also follows directly from the idea that each player's cost is meeting the desired upper bound. So it has to be each player's cost is less than delta I, so we have this upper bound. Two observations we can actually derive here. The total cost in equilibrium will be basically a representation of this bound is given by these the idea that the equilibrium cost can only lie between these two lines. Yeah. Then we also have a question: can players have very unreasonable expectations with respect to their bounds? So this result says that players cannot have players that is total bound on that is the joint expectations cannot be lower than the total cost in cooperation. Yeah. So that is summation of delta I must be greater than the total cost in cooperation. They cannot have this total expectation lower than the cooperative cost. And if we have multiple guaranteed cost equilibria, we can also rank them using this POS measure. So those which are very close to 1 are preferred because they are very efficient, because their efficiency is closer to the cooperative outcome. Okay. So we have these properties. Now the question is, how do we compute these guaranteed cost equilibria in this differential game? So we have the first result, which is basically given the cost profile of the players and a particular strategy profile, when can I say that this strategy profile is a guaranteed cost equilibrium? So we have the following sufficient conditions saying if each player for each player, if there exists a positive definite matrix such that the following linear matrix inequalities hold true, then we say that this strategy profile is a guaranteed cost equilibrium. And we can, so if you see, these are 2n linear matrix inequalities, and it is a semi-definite programming problem and can be solved easily as a convex optimization using the tools like CVX and so on. Okay. But this result cannot be used for synthesizing a guaranteed cost equilibrium. It is only, I can just verify if a strategy profile is an equilibrium or not, but I cannot synthesize an equilibrium. So for synthesis, we require that the guaranteed cost response of each player must be non-empty. Yeah? Just like in computing a Nash equilibrium, we require the best response of each player should be non-empty. So we have a similar condition here, requirement here. So given that is the cost profile of player I and other player strategies, we say that this guaranteed cost response of player I is non-empty if the following matrix inequalities in the variables Fi and Pi hold true. Okay? But these matrix inequalities are bilinear in the variables Fi and Pi, and bilinear matrix inequalities are highly non-convex, and we cannot solve them using, cannot be solved as a convex feasibility problem. But this bilinear matrix inequality has a special structure. It is a Lyapunov inequality. So we can use a lemma called a Schur complement lemma and rewrite this inequality as follows. And the feasibility of this inequality in these variables Fi and Pi can now be written equivalently as feasibility of two matrix inequalities in one variable alone. Okay, so this follows directly from a result called projection lemma. Okay. So what it says is if I have a matrix inequality in these two variables P and F, I can equivalently write the feasibility of this matrix inequality as feasibility of two inequalities in one variable alone. Okay. So if I do that, I get a condition that the guaranteed cost response is non-empty if I can find a positive definite matrix that belongs to a certain convex set, but its inverse should belong to another convex set Y. Okay, so that is basically the characterization for non-emptiness of the guaranteed cost response. But what exactly is this set X? It is a subset of a positive definite cone, and Y is also a subset of a positive definite cone. So we have a characterization as a cone complementarity problem that the guaranteed cost response is non-empty if I can find a positive definite matrix Pi that belongs to a subset of a convex cone, and its inverse must belong to another subset of a convex cone. So that is basically the classical cone complementarity problem. And though I have written now the characterization of non-emptiness is recasted as a cone complementarity problem, but this problem is also non-convex because I can now rewrite this set equivalently by lifting it to one more dimension. We have a bilinear constraint as Pi equal to identity. So that means I cannot also verify the non-emptiness as a convex feasibility problem, but we can relax we can do a semi-definite programming relaxation. I can construct, basically I can relax a set pi to pi bar. I'll be done in 2 minutes. It's okay. And this set is a convex set. Okay? And notice that this set pi is characterized by the condition that all the elements satisfy the condition that the trace of this product is equal to n. Okay? So now I can search in this set pi bar to look for elements which satisfy the condition that trace is equal to n. Okay? But trace minimization problem again is non-convex. So we can solve this non-convex problem through successive convex optimization, algorithms to actually to find if this set pi is empty or not. Okay, so what we are doing essentially with this relaxation, semi-definite relaxation, is that we can actually come up with a sequential convex optimization approach to test if this set is non-empty or not. Okay. So that means now I have a convex optimization based test to verify if the guaranteed cost response is non-empty or not. So now I can use similarly to a sequential best response, we can also devise a sequential guaranteed response to construct this guaranteed cost equilibrium. Okay. This is in principle similar to a sequential best response, but here one difference is the stability requirement is embedded at every step because of the Lyapunov inequality that is a part of non-emptiness of the guaranteed cost response. At the moment, we don't have theoretical guarantees of convergence, so these currently work in progress. So now we revisit the problem where we did not find the sufficient conditions were too stringent to verify if this game had output feedback Nash equilibrium or not. We see that for a delta greater than 0.4, we have guaranteed cost equilibrium. And the lowest POS that we get is 1.01. Yeah. Of course, there are many guaranteed cost Nash equilibria, but the one with the lowest has a POS of 1.01. Now, the guaranteed cost equilibrium is not only for output feedback case, but for state feedback case as well. So now we can also compare the performance of this equilibrium with a Nash equilibrium. So this is a differential game. I have taken it from this book. So for this game, I have only one unique state feedback Nash equilibrium, just unique state feedback Nash equilibrium, and it achieves a POS of price of stability as 1.108. But we have many guaranteed cost equilibria that achieve a POS between 1 to 1.086. In fact, the shaded regions here, these are all delta combinations, that is the thresholds of players that ensure that they have a POS less than that of the Nash equilibrium. So to conclude, we have provided, at least we discussed the concept of guaranteed cost equilibrium in a differential game. We provided conditions for existence and also convex optimization based methods for computing these equilibria. At the moment, we don't have guarantees for convergence, and also we'd like to extend this work to uncertain differential games, and also to study in a discrete time setting. Thank you very much.
So I was wondering, what's your take on numerically searching for a solution in these kind of things? Like you mentioned optimality and suboptimality.
Yeah.
So can you comment on any complexity of the numerics?
Oh, okay. So that's the reason why I'm also talking about sufficient conditions for existence and also convex optimization based methods for computation. At least I can, here the only issue that I cannot guarantee is the convergence of this scheme. that is with respect to computation. But this, but if okay, this approach that I mentioned about the convex optimization based approach, I mean, if it converges, I know for sure that the guaranteed cost equilibrium exists. Here, if you're talking about the number of solutions, then we also did, if you remember, there is a measure that is going to rank the number of, that is going to rank the efficiency of this equilibrium, that is going to rank this equilibria with respect to its efficiency. So if there are multiple, I can rank them with this measure and choose the one that is close to 1.
So you are able to talk about the existence of, but not about the uniqueness.
No.
So you are getting a continuum of equilibria or multiple isolated equilibria?
Here I am actually getting continuum of equilibria, because notice here these equilibria are characterized by inequalities, right? In the sense, the feasibility, the region where it's going to exist is, here I'm not solving a minimization problem, I'm just looking into all the set of strategies which ensure that this cost, that is this function, is below this delta I. Yeah. So this is not, here I'm not really looking for a uniqueness kind of, mostly I get a continuum of equilibrium.
So one more clarification is, so if your PI matrices, positive definite matrices, you're able to find out. So does that mean always cones X and Y will exist?
Can you repeat again?
If, for example, for a problem, you're able to find out PI.
Yeah.
So it means you have this guaranteed cost Nash equilibrium, but these cones X and Y, they will exist.
These sets, you mean?
Yes, that complementary.
You mean these sets?
Yes.
See, these sets are completely characterized by the problem data. That is A, B, and you see this, that is what I mentioned. A, B, C, Q, and R, that is a problem data, is going to determine those sets X and Y.
So since we are already running behind time, maybe we can continue the discussions outside. So let's thank Vishwanath again.
Thank you.